In this presentation, we consider objects that are no longer treated as point masses, but instead we have to look at them as rigid objects. A rigid object is basically an object that can't be deformed, or we don't change its shape in any way. And we want to look at what happens when we apply a force on that large object that is at some distance from, let's say, an axis of rotation. So the first thing that we have to think about is that the rigid object is non-deformable, so it's always going to stay the same shape, and the points that make up the particle always remain in a fixed position on that particular object. So you could imagine that if you had a solid sphere that was made of something, there's little tiny particles that make up that sphere, and they always stay fixed where they are on the actual object itself. Realistically, all objects are actually deformable in some way, so we're using this as a model. This is kind of like our ideal world where we don't have friction and that sort of thing. We always start with the easiest case and then build on that. So obviously, the place that the force is applied on an object can have an impact on its motion. So as another example, if I had like a beam or something like that, and I were to apply a force at the very top of that beam and it was sitting on the ground, that can have an impact and it can cause this beam to, fall over. On the other hand, if I took that same beam and I applied the force down low, maybe the beam, instead of tipping over, would actually slide. So that's just an example of how that force acting on this rigid object can have an impact in terms of what will happen to that object, and it'll be different even if the force that's applied is exactly the same. The location is going to have an impact. So let's think a little bit about the fact that if we apply force at some distance, that it can cause this rotation. And it turns out that objects can rotate about different axes. So it's important as we have our discussion that we think about the axis of rotation. So in this particular picture, this is supposed to represent some type of a disc. You could think about it as like a bicycle wheel or something like that, where the axis of rotation goes through the center. And so if I were to spin this, I could give it a push and cause it to essentially rotate about that axis. So the line that goes through the center is representing our axis of rotation, and we'll talk about what that means in a little bit more detail here in a second. On the other hand, you could have that same disc, and there's its center, and we could certainly have it and spin it about a different axis where the axis kind of passes through that horizontal or that vertical line. This would be something like maybe spinning a quarter on a flat surface like a table or something like that, right? So there's different ways that these objects can be impacted by a force being applied, and some of that is going to be related to what is the actual axis in which these points or which this rigid object rotates. All right, so let's think about it for a second and just think about what's going on in terms of an object that is a rigid object that is rotating. So in this particular picture, I have a wheel. This could represent like a CD or something like that you're going to put into your CD player or a DVD. And suppose that it is rotating counterclockwise at a constant rate. So this picture represents a single snapshot of the picture, of the representation. So this whole disc is rotating around in a counterclockwise direction. And so we could ask a couple of different questions. Is the time taken for points B and C to move through one complete circle greater than, less than, or the same as the time that it takes for point A to go through one complete circle? And then based on that answer, how do their speeds actually compare to one another? So if we think about this disc rotating, you could imagine that, here is my axis of rotation is in the center, So I've got some distance from the axis of rotation for B, I have some distance from the axis of rotation for C, and I have some distance from the axis of rotation for B. So as this disk rotates, point B is going to rotate around, point A is going to rotate around, and point C is going to rotate around. And so we're interested in the time taken for these points to rotate through one complete cycle. So let's think about this, since this is a solid object, and since the points are fixed in space, by the time this moves through one complete cycle, they've all moved through one complete cycle, right? A, B, and C. As I rotate this disk around, they're going to end up all moving together. So if I think about a picture at different time intervals, here was the object that's going to rotate around counterclockwise, and here's my points A, B, and C. And as this thing rotates around, this is a picture on the right is where those points would be after it has rotated through half of the cycle, right? So it hasn't made its way quite all the way around, but point B has rotated all the way around so that it's over here, and then point C has rotated all the way around so that it's over here, and then A, of course, has rotated around until it's over here. So one of the things that hopefully we notice is that all those points are rotating together. So the time it takes for them to get back to where they started in terms of going around one complete cycle is the same for all of the points in the picture. So that's going to help us as we look at these rigid objects. The points are always going to rotate through the same angle in the same amount of time. So there's a couple of things that we're going to think about as we go through. So is there a single linear velocity vector that applies to every point on the wheel? So if we were just talking about the speed of the point in terms of the distance covered over the time, do all of those points cover the same distance in the same amount of time? If it's all the same, okay, great. If not, is there a position that has the largest speed? And then we can also ask, for which of these points is the angle change between some initial and final position? Which one of this has the greater change in angle? And then we'd like to also know what is the rate of change of that angle for any point on the wheel. So here's our picture again, or here's another representation of a similar picture of a disk. And so now we have our axis of rotation that's passing through the center. And so this is more of a three-dimensional picture. And we're looking at it where before we were sort of looking down. And so we have some reference line here. And so we can measure points on the disk relative to that reference line. So these are not points A, B, and C. These are new points, I guess, A, B, and C. So I could imagine that if I had this point here, A, that's close, B, and then I have a point C, and this is where they're located at some initial time. After this disk rotates a little bit, this is their new location at some final time, A, B, and C. So I have drawn a line that passes through all of those points, and the reason that I've done that is because I can talk about the angle that all of those points start at relative to the reference line, and I can determine where they all end up relative to that reference line. And so as I look at that picture, all of those points, even though they are different distances from the axis of rotation, all go through the same angle, delta theta, which is the final angular position minus the initial angular position in the same time frame, because they both start at time t initial and end at some time final. So in terms of measuring these quantities, of course, time is measured in seconds, but how do we measure angles? So there's a number of different ways that we can measure an angle. And the standard that we would use to measure angles is radians. Because radians, and I'll talk a little bit more about this, is actually not a physical unit. It's actually dimensionless, but we put in radians to represent the fact that we're talking about an angle. Other units that we might use to represent an angle might be degrees. We could talk about this disk going all the way around 1 revolution. In one revolution would be 360 degrees, and so another representation would be revolutions. So you could talk about the object moving through 1 revolution, which would be all the way around, or a half of a revolution, or, you know, or so on, right? A part of a revolution. So where does this unit of radian actually come from? So the angle theta is actually a pure number, meaning it doesn't have a unit, it has an artificial unit. And the angle of radians comes from a measurement on a circular path. So here is my reference line, and then I have my point P. Point P started off here, and then it moved through some angle theta. And as it moves through some angle, it is a distance r away from the axis of rotation. And it moves through some arc length, s. So by definition, the angle in radians is just the arc length divided by the radius, or the distance from the axis of rotation. And because these are both units of length, meters over meters, this is actually a unitless quantity, but we give it an artificial unit of radians so that we know that we are talking about specifically degrees, or not degrees, but an angular measurement. 1 radian is the angle that's subtended by an arc length equal to the radius. That's kind of a weird description. Certainly one thing we can think about is the relationship between angles and revolutions and degrees. And so if I go 1 revolution, so I go all the way around 1 time, then the angle that I go through is equivalent to 2 pi radians. And if we think about where that's coming from, my arc length would be the distance all the way around this entire circle from that point, and that distance would be 2 pi times the radius, or the circumference. So if I calculated the angle, which is the arc length divided by the radius, this is 2 pi times the radius over the radius, and I get 2 pi. So 1 complete revolution is equivalent to 2 pi, or 360 degrees is equal to 2 pi radians. So that's where those relationships are coming from. So we can certainly write those down in terms of if we needed to convert units. So we know that 1 radian, or 2 pi radians, is equal to 360 degrees, going around once. And so we can use that relationship, and we can write this as 1 radian is 360 degrees over 2 pi. And that's where we're getting this 57.3 degrees approximately. So if we want to convert between radians and degrees, we can use that conversion factor. We can also use a conversion that 1 revolution is equal to 2 pi radians. But keep in mind that the standard unit that we would want to use, especially when we're talking about physics and comparing motion that's related to translational motion, moving from one place to another, and rotation, everything needs to be in radians. All right, so we have something now that we can define as our angular displacement. So our goal here is to look at rotational motion to start with, and go back through all of the different descriptions of motion that we've already covered so far, such as position, right? And in one dimension, acceleration, got a little ahead of myself there, right? Acceleration, velocity, right? And so on. We talked about kinetic energy, momentum, and all of those different things. So we'd like to go back through and look at rotational motion where we don't have any sort of translational motion from one place to another, and just consider what's happening when it rotates. So we can define something called angular displacement, which is basically just the angle that a point or a solid object rotates through from some initial angle to some final angle. And this is going to be very much equivalent to the regular displacement, which is just the difference between your final position and your initial position, where this is just in a one-dimensional picture, you know, your initial and your final positions, something like that. We have to have a reference line here, and so in this particular case we've drawn an x-axis. The rotation is counterclockwise, and so we can see that it's sweeping out this distance, and that we have some starting angle and some final angle. So if we have this angular displacement, we can also define something called angular velocity. So if we go back to our definition of just linear velocity is just a measure of the displacement over the time. So if I start here and I end up at some new position, like this, right? Then I have covered some displacement, and that has occurred in some time interval, and so I have this average velocity. So in a similar way, if I have a solid object that's spinning, I could talk about its angular velocity, and we write the angular velocity in this as an omega. And so for any one of these points on here, they all start at the same initial angular position, and then after some time they have moved through to a new angular position, right, where their new angular position is essentially the entire angle here, final. So no matter which of those points that I look at, A, B, or C, they all go through the same angular displacement in the same amount of time. So if this is where they started initially and this is where they end up, then the time interval for that displacement of any point, and it could have been any point on that disk or any point on the rotating object, and they would all go through that same angle in the same amount of time. So we can define the average angular velocity as the angular displacement, the angle that it goes through over the time interval. And so in terms of units, the units for the angle, the standard would be radians over time. So the angular velocity is going to have units of radians per second. So I covered this on the last slide, but this is just how we could actually write it. Specifically now we're talking about an average. So what we're going to find is that all of the variables that we had for linear motion, we also have for the angular motion. Of course, if we wanted to talk about the instantaneous angular speed, that would be, you know, how fast is it spinning at a particular instant in time, then we would have to look at the limit as the time approaches zero, and that change in the position, the angular position over time, becomes a derivative, and we have to look at how that angle is changing over very small time intervals. Angular velocity is actually a vector quantity. So it is a vector. And so we have to think a little bit about the fact that it's a vector. And so when you think about an object rotating about a particular axis, let's say I have this disk here, and here's my x-axis, and here's my y-axis, and this disk is spinning in the counterclockwise direction. That's considered the positive direction. So this would be positive angular velocity. And then if on the other hand, the object was spinning clockwise, that's considered the negative direction, and so that would be negative angular velocity. So we do have this vector component of the angular velocity in terms of it being positive or negative with the rotation. We're going to be a little bit more specific on this in a minute. We also might be interested in what is the linear speed of a point on this disk? And that was part of the questions that we started with. So do each one of these points, A, B, and C, travel with exactly the same speed if we're just measuring speed as distance over time? So I always like to give the example that imagine that you have a bunch of people holding hands, so person A, B, and C. So they're holding hands here, and they're all staying very rigid along that line, and they're going to spin around in the circle. Would person A have to move as fast as person C in order to keep that rigid line the same? And the answer to that is no, they would travel at different speeds. So if I go back and I measure their distance covered, so A covers a smaller arc length than B as compared to C. So this would be the arc length of C, the arc length of B, and the arc length of A. So each point covers a different distance. And since we know that velocity in general is the distance covered over the time, then we know that there should be a different speed of those objects. And so it turns out we call this tangential speed. We'll come back to this in a little bit, but it's tangential speed because at any point in the motion, the speed of the object or the velocity is tangent to the path. So there would be this tangential speed of C, tangential speed of B, and a tangential speed of A. And of course, the further out you go, the faster that you're having to actually move. So we'll come back and talk about that a little bit later. Finally, we can also have angular acceleration. So if we go back to our linear acceleration, the linear acceleration is a measure of the change in the velocity over the change in time. So if the motion is not uniform, if it's not moving at a constant speed, speeding up, slowing down, changing direction, then we have acceleration. So in a similar way, we could have a representation of this disk which is rotating around in the counterclockwise direction, and each one of these numbers represents where those particles are, or those parts, I guess, of the bigger object, solid rigid object, and where they are over equal time intervals. So between 1 and 2, they all cover the same distance, delta theta 1, I'll call it. And then in the next interval of time, they're covering more distance, delta theta 2. And then finally, by the time they go into the next time interval, they're covering even more angular displacement. So because they're covering more angular displacement over time, they must not be traveling at a constant angular speed. So this object's rotational motion is speeding up. And if it's speeding up, it must have acceleration, and so we define this term called angular acceleration. And angular acceleration measures how the angular velocity changes with respect to time, and of course we're talking now specifically about an average. So if it's spinning at a constant rate, then that means that the velocity, angular velocity it has to start with is the same as it has afterwards, and this would imply the angular acceleration is 0. And that's similar to an object moving across a straight, flat surface. If it's moving at a constant speed in a linear motion, then it's going to have 0 acceleration as well. So we have this definition now of angular acceleration in terms of our angular variables. In terms of units, the angular velocity would be measured in radians per second. The time would be measured in seconds, and so the standard unit for angular acceleration would be radians per second squared. And so that's similar to linear motion. And so for linear motion, the units are meters per second squared. So we sort of have this analogy between linear motion and rotational motion, and everything we've learned about linear motion we can sort of reapply to this angular motion, or rotational motion. Of course, that was the average acceleration, angular acceleration. So we could also talk about the instantaneous angular acceleration. So we would have to look at what happens to the average over a very small time interval. So what is that average acceleration? How does the angular velocity change over a small time interval? And then what happens, of course, is that becomes a rate of change of the angular speed with respect to time, and we would have to take a derivative. So just some general things to keep in mind. We have now defined angular position, angular velocity, and angular acceleration. For a rigid object, all of the points on there at any instant in time will have the same angular displacement, the same angular speed, and the same angular acceleration, right? So we've been drawing these disks, and we could look at points on here at any location, and I could define a particular angular displacement from over some time interval, and it would be exactly the same for all of those points on here. If I were to look at how far they moved in a given time interval, at any instant in time they would have the same angular velocity and they would have the same angular acceleration because the object is rigid and all the points spin together. So the other thing that we need to talk a little bit about is how we actually define angular velocity and angular acceleration as a vector. So if we have a solid object that's spinning, so in this particular case we have a sort of an axis of rotation here, and then we have a disk that's rotating around this direction here. We can't just keep drawing these pictures to represent the motion in terms of just drawing an arrow that rotates around and say it's clockwise or counterclockwise. So the way that we actually represent the direction for angular velocity and angular acceleration is such that it is a vector that is perpendicular to the actual rotation itself, and it's going to be along a line that is the axis of rotation. So in this particular case, I have an axis of rotation that's going along this rod, and the object is spinning to the right or going around. And so the way that I can determine that the velocity vector is pointing perpendicular to that rotational motion is by using something called the right hand rule. So if you wrap your fingers around in the direction of the motion, your thumb will line up with the direction of the angular velocity. So if the object was spinning in the other direction, your fingers would have to wrap around the other direction. You'd have to turn your hand upside down and your thumb would point down, and so the angular velocity would be in that direction. And we can do the same thing in terms of angular acceleration. So basically we've learned that the angular velocity is going to be along the axis of rotation, and so By convention, its direction is out of the plane of a diagram when the rotation is counterclockwise. So if I draw a picture like this and the object is rotating around, then the direction of the angular velocity here is out of the screen. And if you imagine, I can't do this in the video, but if you just plop your right hand down with your fingers in the direction of the rotation, your thumb will point up out of the screen. And then obviously if it was rotating the other way, if you were to try to put your fingers of your right hand in the direction of the motion, your thumb would point into the page. The direction of the angular acceleration is going to be in the same direction as the angular speed or angular velocity if the angular speed is increasing, and it's going to be in the opposite direction or anti-parallel if it's decreasing. So this is similar to translational motion, where if you have an object and it is speeding up, then the acceleration is in the same direction as the motion, and if instead it is slowing down, then the acceleration vector is in the opposite direction, right? So this is v initial and v final. And so it's the same thing here in terms of rotational motion.